So far in this day worth of lectures, we've been discussing a lot about parallel plates, and now I'm going to actually talk about what a parallel plate is and what would be the purpose of a parallel plate, okay? So we're going to learn about something called capacitance, okay? And capacitance is when you have a device that can store electrical charge, and we call that electrical device a capacitor. Okay, and so the purpose of a capacitor would be to, store an electric charge so it could all be released at once. So one of the a common example that makes the most sense to me is like a camera flash. So a camera flash, when you turn it on, it makes this sort of noise. It goes ooh, and that's actually the capacitor charging up, okay? And then you can release all the energy that you've stored on that capacitor in a quick sort of flash of a charge, right? And it creates this bright light, okay? So let me just kind of draw what this looks like, and then I'll actually show you a capacitor, right? So again, we have this whole situation where we have two parallel plates, okay? And imagine, I keep drawing them like this, but imagine there are two sheets of metal sort of like sitting like this. That's what a parallel plate capacitor is, okay? And when you construct a parallel plate capacitor, there's two things that you take into consideration. How far do you separate the plates from one another, as well as the surface area of the plates. So the surface area, which we write with the variable a, and the distance between the plates. Which is d. Okay, and so we'll kind of come back to that later. So essentially what you do is you have these two plates, and in order for them to be sort of reasonable in size and to sort of fit nicely into electronic equipment, we actually kind of roll them over on each other, okay? So you make sort of this like I don't know, it looks sort of like a Swiss cake roll to me, right? Where you have these two lines here representing the plates, and then the black is supposed to be an insulator in between the two plates as they've rolled over, so there's no crosstalk between the plates as they roll over each other, okay? And if you want to, this is actually a capacitor, right? So you can see here that it looks sort of like a Tootsie Roll, so it's rolled over on itself, and then there are two wires coming out of the end, and those two wires are actually what's going to hook up to whatever your voltage source is, to the battery or the wires in the electrical outlet, okay? And it says on here, you probably can't really see that. Let's zoom in a little bit and see if you can see. So on the side of it, it says, and I can kind of hold it still. Yeah, you can't really see that, but it says 1,000 microfarads, and so we'll talk about what that means in terms of capacitance. Okay, so essentially what you do for a parallel plate capacitor is you're going to hook those two little wires up to some sort of voltage source. So in our case, we'll just consider a battery, right? So let's just say this is a 12-volt battery, okay? And you know that batteries have positive and negative terminals. So we'll say this is the positive terminal and this is the negative terminal. And then we have another wire hooking up to the other side of the plate. That's why this thing has two little wires sticking out of it, okay? So essentially what would happen is if you have a metal here, and electrons, remember, are free to flow in metals, and you hook it up to a battery, the electrons from this plate are going to be attracted to the positive side of the battery. So electrons are going to start to flow in this direction, okay? Then electrons are also going to be repelled by this negative side of the battery, so electrons start to flow in this direction too. So as electrons leave this plate, you end up with a net positive charge, okay? And as electrons are added to this plate, you you end up with a negative charge. Okay? So capacitance is really the amount of charge that something can hold per unit voltage. So we define it as Q, being the charge, remember, is equivalent to the capacitance of the capacitor, sort of like how much can it take per unit voltage, right? So it's charge over volts is what capacitance is, right? So this is how you can calculate the knowing the capacitance, which is, this is a property of the parallel plate. Okay, and we'll go back to this to explain how we know that. The voltage is based on what your source is, right? So the battery or the electrical outlet, whatever. And what's important to know is if you let a capacitor fully charge, you end up with a potential difference here of 12 volts, right? So whatever the voltage of the battery or the source is going to be the voltage difference here. And so that can tell you how much charge you can put on the plates. Okay, so how do we determine the capacitance of a capacitor? Okay, so capacitance is written, so if I solve for this, it's Q over V. Okay, so Q over V is capacitance. So that is coulombs. All right, coulombs, just so we don't get confused. Let me get the lights back on. Coulombs over volts, right? And that is actually called a farad, which is written with the letter F, okay? So, but how do we figure out this value? Like we said, it's a property of the plate, so where does it come from? Well, it all has to do with this, the surface area of the plate and the distance between the plates, okay? So the equation is this, and the equation really makes sense once I'll kind of describe it here in a second, okay? So imagine if you are building a capacitor. If you make the plates really big, you're going to be able to store more charge, right? So surface area equals a greater capacitance, okay? As you start adding electrons onto a plate, they start to get crowded, right? So once they start to get crowded, they start to repel each other. So the bigger the plate, the more electrons you can add on before that repulsion of the electrons balances the push that's created from the battery. Okay? Now, the distance apart, why does that matter? Well, if you look here, what is essentially starting to happen as we hook the battery up is we start to have a positive charge here and a negative charge here. So in fact, this big positive charge sitting here helps to pull the electrons in this direction. And we know electric force is relative to distance, okay? So the closer in proximity these two things are, the stronger this positive charge is going to have a pull and the more electrons we're going to be able to add. The further apart they are from one another, the less this is going to influence the amount of electrons they can have. And that's why D is on the bottom. So if D is very large, you have a big distance, the capacitance is smaller. If D is very small, then the capacitance is bigger, okay? And then remember we have this E sub naught business. That's the permittivity of free space. It's a constant. It's just all about the ability of electrical force to sort of span, you know, a space, okay? So the construction of a capacitor affects the capacitance or determines the capacitance. And the amount of charge stored on a capacitor is relative to both the capacitance and, you know, the source of the force.